welcome all of you on behalf of Ramakrishna Mission Institute of Culture. With the permission of Swami Suparnanandji, Yadavindranathji, I welcome you again in today's lecture and interaction sessions. We were waiting we're a couple of minutes late because we were waiting for some students to arrive. We think they will arrive soon because we kept some seats here empty for that reasons. But there are plenty of seats available, so that won't be a problem. Now, today we have the pleasure of introducing an excellent speaker and distinguished scientist and professor, Professor Ashok Mallik, and who was in IIT before, right now at BESU. And BESU is honorary distinguished professor, and IIT was regular professor. And so he will be giving a talk, as you know, on something that Ramanujan did. Ramanujan, all of us know, actually, I heard the name, I'm sure, but many people do not know exactly what he did. And Professor Mallik has uncanny capability to make things very simple. And in a very simple way, he will try. I heard his lecture before, so I know. So he'll try to explain to us, at least give some ideas of what he did to the audience. I'm sure that all of you will enjoy that one. And then as a formality, I'll make some announcements about his qualifications and things like that. And I'll try to read, and sometimes I may skip some of the reading part of it. Originally, he's a professor of mechanical engineering. Mathematics was his hobby. And of course, you needed mathematics for mechanical engineering quite a bit. But he really, excelled. Is it okay? He excelled because of his, love for mathematics. He has many short lectures prepared. Not short, 1 hour lectures prepared on various aspects of mathematics. And this is one of them, the Ramanujan's contributions. And he was the first occupant of S. Sampath Institute Chair professor, established in 2006 in IIT Kanpur. He was a Commonwealth Scholar at Institute of Sound and Vibration Research at Southampton, England, and an Alexander von Humboldt Fellow at TH Aachen and TU Darmstadt, Germany. He is the recipient, which is, I already mentioned, but still, it shows how good a speaker he is. He's a recipient of the Distinguished Teacher Award of IIT Kanpur. And so he was a very popular teacher, among the students. And he has the fellowships from almost all the major academic institutions in India, such as INSA, Indian National Science Academy, and National Academy of Engineering, and National Academy of Sciences, Allahabad, and Indian Academy of Sciences in Bangalore, and INSA of New Delhi, as I said. Right now, he's an honorary, I told already, he's an honorary distinguished professor at Indian Institute of Engineering, Science and Technology, Shibpur right now. He's also an honorary fellow of the Associations of Mechanisms and Machines for his lifetime contributions in the field of theory of mechanisms and machines. He has authored, co-authored 9 books and more than 85 research papers in international journals. Areas of his research include vibration engineering, nonlinear dynamics, and kinematics. He also writes many articles and books, popular articles, on mathematics and physics at popular level. So this is his background. I just wanted to share with you before he goes for talking. And I'm really honored to introduce him. And so I will request him, our respected Swamiji, Suparnanandji, and the speaker to come on the desk, and come on the desk actually, both of you. Would you please come to the desk, Maharaj? request Swamiji to give him some books as token of our appreciations to the speaker for his time and help. We are grateful to Swamiji for coming, though he was leaving actually. He's very busy today, but he came here just for the talk. But I don't know how long he'll stay. Okay, wonderful. So I'll leave the dais for the speakers. Please start your talk in that case. After the talk, we'll have questions and answers. So please, one at a time, please ask the questions. You raise your hand, and then somebody will take the microphone to you. So that not only you know the questions and the speaker, but everybody knows the questions and then answers, so that you could enjoy the answers. So you can pass the questions after about an hour of his lecture. And I'm sure that we'll be very happy to interact with you for any clarifications or comments. Thank you very much.
Thank you, Professor Lahiri, for the kind introduction today, and I owe him some special thanks because he is the person chiefly responsible for arranging this talk and introduced me to the Vivekananda Science Circle. Today's topic is written here, some magical mathematics, so I'll discuss more of magic and less of mathematics because I'm not a mathematician. Ramanujan is the best mathematician that India has produced in the modern era. He was born on 22nd December 1887 and died very young in 1920. Besides this short lifespan, there are three other things I would like to mention so that we can all appreciate the genius of Ramanujan. It is not only short lifespan, he had to surmount three other almost apparently unsurmountable difficulties. The first one is he had financial trouble almost throughout his life. Second, he had some serious health problems during the peak period of his mathematical activity. And thirdly, he never had formal training in advanced mathematics. But by sheer genius of Ramanujan, not only overcame all these difficulties, he created mathematics of lasting impact with his creativity. His contemporary mathematicians used to rate his innate mathematical ability just to the level of Gauss and Euler. There is a beautiful biography of Ramanujan entitled The Man Who Knew Infinity, written by Robert Kanigal, who is a professor of history of science at MIT. Actually, Ramanujan had uncanny ability to rattle out the special characteristics of any number very quickly. So much so that British mathematicians said all natural numbers were his personal friends. So he knew them very intimately. Ramanujan's mathematics always had some mystical or magical approach to solving problems. And I think I'll start this magical approach with a magic square. We all know what is a magic square. This is a 3 by 3 magic square. As you see, the numbers 1 to 9 are written in such a way that if you add the numbers in a row, any particular row, or any particular column, or along the principal diagonals, you get the same sum, namely 15. 8 plus 1, 9 plus 6, 15. Similarly, 7 plus 2, 9, 6, 15. 6 plus 5 plus 4, 15. This is a 3 by 3 magic square. Actually, there are only three very simple rules which all of us can remember so that we can fill up any magic square of odd order, like 5 by 5 or 7 by 7 or 9 by 9. The rules are very simple. You write one of the top central block. Then always try to go diagonally to the right in an upward direction. So if you write one here, you go diagonally to the right, you go out of the magic square by crossing this boundary line. In such a situation, you go to the other extreme and write the next number here. So I write 1, I go there because I am gone out, come down here, 2. Then again I try to go diagonally right, again I go out by crossing this boundary line, so I go to the other extreme, right 3. Then I try to go again upward, then I get the second rule. If that block is already filled up, then just come down. Because 1 is already written there, I come down, 4, I go diagonally up, 5, diagonally up, 6, diagonally up. I go out, but don't cross the boundary line, I cross this corner. If I go out through this corner, then I again just come down. So I write 7, then go out, crossing this boundary line, so I go to the other extreme, then go up, getting the boundary line, so go to the other extreme. So just 2-3 rules I have to remember. Like 5 by 5. Just let us go through quickly. 1, 2, 3, 4, 5, is filled up, 6, 7, 8, 9, 10, filled up, so I come down, 11, 12, 13, 14, 15, I go out to the corner, so I come down, 16, I go out, 17, go out, 18, 19, 20, is already filled up, 21, 22, 23, sorry, I go out, 23, 24, go out, 25. So it's a very simple rule to fill up any odd order magic square. And that's why mathematicians are not interested in it, because the problem has been solved. Real interest lies in even order magic square. Here there is no such mechanical rule. Not only that, there are enough possibilities. That's why it has drawn attention of not only mathematicians, even some non-mathematicians who are obviously very special people. Like magic square of even order. This is Benjamin Franklin. As you know, he was not known as a mathematician, but he was a scientist, inventor, statesman, printer, philosopher, musician, economist, he was a polymath. Benjamin Franklin, in 1769, when he was, 63 years old, sent a letter to a colleague containing an 8 by 8 magic square. This is the Benjamin Franklin's magic square from 1 to 64. You write 1, 2, and 3 somewhere, 64. The property of this magic square is, if you add the rows or any column or any rows, then it will add up to 260. But it fails about the principal diagonal. Principal diagonals do not satisfy the magic square requirement. But it has some other special properties. Like, as you see, this shaded portion, this is the broken bent row. It is not a straight row, it is a broken bent row. If you add all these numbers, again we will get 260. If I add all these numbers, again we will get 260. If I add this, you put there, then this and this, again we get 260. Not only that, if I take a 4 by 4 subsquare, I can get 4 by 4 subsquare, 4 of them. One here, one there, one there, one there. There also, the rows and columns will add up to just half of 260, that is 130. So it is a very special 8 by 8 magic square, but it fails the principal diagonal condition. But the most famous magic square of even order belongs to a German famous painter, Albrecht Durer. In 1514, he found a magic square, and then he drew one picture which is called Melancholia. This is painting of his 63-year-old mother, and probably from a distance you can see or not, I don't know. Here is a 4 by 4 magic square. This is a wooden work in his house, 4 by 4 magic square. Because he was so proud of this magic square, he included it in his picture. Why? Let us see that. This is the 4 by 4 magic square from 1 to 16. And if you add up any row, any column, and principal diagonal, they will give you 34, I think. Yes, 19, 21, 34. So that is very simple magic square. But what he found, that if you add all the diagonal numbers, extreme n numbers, then also it will be 34. 16 plus 13, 29, 30, 34. Not only that, If you add these 4 or these 4 or these 4 or these 4, again it will be 34. Not only that, if you have 8 plus 3 plus 9 plus 14, you leave out 2 in between. You skip 2. Then also it will add up to 34. If you add up these 4, it will add up to 34. And if you add these red ones, again skip 2. They will also add to 34. Diagonals I have already said they add up to 34. Not only that, if you add these 2 and these 2, you get 34. These 2 and these 2, you get 34. And of course, this is already said. So whichever way you almost combine, it adds up to 34. This is the last one, I think. 8 plus 2 plus 9 plus 15 again is 34. 3 plus 5 plus 14 plus 12 is 34. So 1 to 16 were written in such a way that so many ways I gave the same total 34. So Durer was very proud of his magic square. But Ramanujan being Ramanujan, he said, I will not write from 1 to 16. He first column, row, he filled up with his date of birth, 22nd December 1887. So 22nd December 1887. And he filled up the other 12 so that it has all the properties of Durer's magic square. That means you add any column or any row, principal diagonal, you get 139. Not only that, if you add all the diagonals, just like Durer's magic square, if you take all the extreme corner points, then also it will be 139. If you add this and this, 139, these 139, these 2 and these 2, 139. Same way, red ones, blue ones, all will be 139. This is Ramanujan's magic square. This is of course 139. Up till this, it is just as Duer's magic square. This is also, these 4, these 4, these 4 and these 4 also will be 139. And the last one that we get is these 4 and these 4 are also 139. And this is more than Albert Duer's magic square. If you remember, no one can remember, this is the Duer's magic square. If you see 10 plus 5, 15, and then 9, 24 plus 6, 30. This is 30, not 34. And this is 38, not 34. But Ramanujan's magic square, these 4 and these 4 also gives you the same total, 139. So this is Ramanujan. I mean, no one knows the method. Okay, so that is what we discussed about Ramanujan's magic square. Now let us see again Ramanujan's on intuitive leap. We all know Pythagoras theorem. So, and Ramanujan did something with that. Ramanujan didn't do much work in geometry, and this work also, as you see, is not geometry, but it starts with geometry. Suppose we have a right angle triangle ABC. This is the hypotenuse, and this angle is 90 degrees. The length of the sides are A, B, and C. We all know Pythagoras theorem that C square is A square plus B square. Now we get a point Q such that BQ is A, and we get a point P such that CP is B. I take this circle, I take this circle. So I get P and Q on the hypotenuse. What Ramanujan said, you can show that PQ square will be 2 times BP into CQ. It is very simple, there is really nothing big in it. BQ, as we see, is C minus A. Sorry, BQ is A and CP is B. And BP is this minus CP, that is C minus B, and CQ is C minus A, and PQ is BQ minus BQ minus BP, that is A minus C plus B. So you can easily check this, that with this result, PQ square will be twice BP into CQ, if we remember Pythagoras theorem, that C square is A square plus B square. You can expand this A square plus B square plus C square, and 1 C square you write A square plus B square, so you get 2 C square, and the product terms comes easily. Now what Ramanujan says, if I write C as square root of A square minus B square, this geometrical result is equal to this algebraic identity. Here there is no C, that means no triangle. It is A and B, any two numbers, These results equivalent to this algebraic identity A plus B into this. Okay, even this is not really magic. This probably, lesser mortals can do. But the intuitive leap of Ramanujan is this. He immediately writes for Q. Let's see. The previous equation, as you see, here we had square root of A plus B whole square. So he writes cube root. Here I have square root of A square plus B square, he writes cube root. Only change he makes A square minus AB plus B square, and square is cube. 2 is 3. This square root is cube root. A square plus B square is A cube plus B cube. That means all 2's are replaced by 3. Only change is instead of A square plus B square, he writes A square minus AB plus B square. And then this is the result he gets just from extrapolation from here. And it will take quite some time to prove this algebraic identity. Now, this is a number which is known as taxicab number 1729, because this is a cartoon that his mentor and collaborator in Cambridge, Godfrey Harold Hardy, went to visit Ramanujan in a London hospital when he was very sick in Putnam area, and he took a taxi whose number was 1729. Just to cheer up Ramanujan, he told, Ramanujan, I came by a taxi and the number was very dull. It doesn't have any special property. He said, what was the number? So Hardy said, number is 1729. Immediately Ramanujan said, oh no, it is a very interesting number. This is the smallest number which can be expressed as sum of two cubes, namely 10 cube plus 9 cube, 12 cube plus 1 cube, both are 1729. There is no number less than this which can be expressed two ways as sum of two cubes. So it looks like magic, but really it is not magic. Ramanujan could say it because he studied these numbers in great detail in India, which was in his notebook. Let us see what. So we all know the famous Fermat's last theorem or conjecture that x to the power n plus y to the power n equal to z to the power n has no solution for integer values of x, y, z and n greater than 2. We know 3 square plus 4 square is 5 square. But I can never write x cube plus y cube equal to z cube, where x, y, z all are integers. So that was Fermat's conjecture. It was proved recently, after 300 years, in 1993, it was proved. But what Ramanujan said, okay, maybe that is true what Fermat said, but can I find x cube plus y cube is z cube plus 1 or z cube minus 1? That means the equation is not satisfied, but just slightly defective, plus 1 or minus 1. Can I find x, y, z? So, and there he said, yes, I can find this. So this is 1, which he wrote 1 cube for Hardy. X cube plus y cube is z cube plus 1, and x cube plus y cube is z cube minus 1. But 1729, he wrote that 1 as 1 cube. Then he said, this is the smallest number which can be expressed sum of 2 cubes. But Ramanujan getting this example is not maths. It is just, arithmetic. He said, can I generate more such combinations? And that is where his genius comes. His identity is from his lost notebook. This is his handwriting. He wrote that 9 cube plus 10 cube is 12 cube plus 1. This is one example. Then he found an equation that if I have this polynomial expressed as polynomials like this, then a n cube plus b n cube will be c n cube plus minus 1 to the power n. Okay, this is difficult to read, so I go to this. This is, tight, not his notebook. He said, if this is so, then a n cube plus b n cube is c n cube minus 1 to the power n. So if n is even, then it will be plus 1. If n is odd, then it will be minus 1. And then, you see, in 2004, somebody completed the work to get the formula for a n, b n, c n, which Ramanujan wrote the first few. These were wrote by Ramanujan, and now he has generalized. That is almost 100 years later. So, okay. This is not the only thing he did. Actually, Euler showed how to solve systematically equations of the time a cube plus b cube is c cube plus d cube for integer values of a, b, c and d. What Ramanujan did, the following formula. He said, if u and v are arbitrary integers, positive or negative, and then we define 4 more quantities in terms of u and v. A, B, C, D is expressed in terms of u and v. Where u and v can be any integers, positive or negative. Then it will be always true. A cube plus b cube plus c cube will be d cubed. I mean, obviously, without being a great genius, no one can think of such, manipulations. So with u equal to 1 and v equal to minus 2, you put u equal to 1 and v equal to minus 2. You will get a equal to minus 27, b equal to 36, c equal to 3 and d equal to 30. And then a cube plus b cube plus c cube is d cube. So we write minus 27 cube plus b cube is c cube plus d cube. Then you divide by 3 cube, you get 1 cube plus 12 cube is 10 cube plus 9 cube. That is the Ramanujan's equation. 10 cube plus 9 cube is same as 12 cube plus 1 cube, which is 1729, the taxi cab number. So he had this combination in various ways. He played with this while he was in India. But he could recall as soon as Hardy told that number 1729. So it appeared as magic. But it is really hardcore mathematics, not magic. Let us see how difficult these kind of problems are. These are 2 famous Indian mathematicians. He was in Cambridge and he was considered just next best to Ramanujan in Cambridge as Indian mathematician. And Sarvadaman Chawla, he spent most of his time, sometime in Cambridge and most of his time in Princeton Advanced Center. So in 1929, Chawla wrote to Pillai that we want to extend Ramanujan's work. He said, this is the smallest integer that can be expressed as sum of 2 positive cubes in 3 different ways. Not 2 different ways, but in 3 different ways. Then instead of 1729, this will be the smallest number. He wrote it in 1929. But it is actually the 4th smallest number. He made a mistake. With computers, now one has shown that this is the 4th smallest number. There are 3 before that. For example, this number is this cube plus this cube, 228 cube plus 423 cube, 255 cubes, 414 cubes. So this can be expressed as sum of 2 cubes in 3 different ways. But Chawla said this is the smallest, but that happens to be the 4th smallest. Now, following Fermat, because he said x cube plus y cube cannot be equal to z cube, Euler conjectured that there is no integer solution a to the power 4. He said, Fermat said x cube plus y cube cannot be z cube. So Euler conjectured a to the power 4 plus b to the power 4 plus c to the power 4 cannot be equal to d to the power 4, where a, b, c, d all are integers. So this conjecture, lived for more than 200 years because nobody disproved it, nobody came up with a counter example. Mathematics, there are 2 ways. Either you disprove, you find a fault in the proof, or you produce a counter example, then you need not prove anything. One counter example is sufficient to kill however famous the theorem may be. So, after more than 200 years of Euler, Noam Elkis of Harvard University found a solution of this equation with a equal to this, b equal to this, c equal to this, and d equal to this. So Euler's conjecture is wrong. Now, mathematicians have this habit, it's a very, I would say, pet constant of mathematicians, pi. It's a fantastic universal constant in mathematics, and mathematicians are, enchanted by it. So, they always wanted to approximate pi, and the first series which was given by Gregory and Leibniz, pi by 4 is 1 minus 1 by 3. It's very easy to remember. Reciprocal of all odd integers with alternating signs. So it will be pi by 4. In fact, this is the only series for which even Newton appreciated Leibniz. Normally, Newton and Leibniz always fought. But for this formula, even Newton appreciated Leibniz, at least for once. Well, this is a good formula, very easy to remember, but almost useless. Because you need 512, sorry, this is important. The same series was also obtained by Nilkant Somayaji in 1500. That means more than 150 years before these Western mathematicians. This is Kerala school of differential calculus, which is now accepted by the Westerners, that, Kerala school invented differential calculus 150 years before Newton and Leibniz. But this series is useless because 500 terms are necessary for an accuracy of 3 decimal places. This number, if I want to calculate accurate up to 3rd decimal place, then I need 500 terms. So there are other series. This is very nice